Okay, I'm technically live now, so just be aware. For people who, well, last week we were having a uh, review session similarly, and I think there was a lot of what do you call the bystander effect, where I would ask anybody to pitch in and maybe interact a little bit or take a guess, and very few people would take me up on it. I think that when there's a lot of people, it tends to create a lot of nervousness and not wanting to sound dumb or not wanting to speak out a wrong answer. So the two people we have so far, um, basically this time around, I was hoping to like maybe do this as a small group of maybe three people, um, who I designate to talk in a maybe more conversational style, with the hopes that it's more interactive and I'm not just rambling for extended periods of time because I have no clue if students are following along. Does that sound okay? I
Yeah, that sounds okay, but I'm not too good at math, so I might
All right,
give a lot of wrong answers.
alrighty. Well, I guess we can take a look. By the way, can you all see my screen at this point? Can you see my screen?
Are you? Yeah,
I'm
I
screen
can.
sharing. Okay, so what I'm going to do is I always like to use slightly different numbers just to make sure that we're focusing a little bit more on the concepts rather than explicitly giving out answers. Um, right. Part of it is academic honesty, and part of it is just I prefer people to engage that way. For this particular homework set, because things are very sketch heavy, it's not going to matter as much, but I'll still try.
Oh,
So, do you all understand what the idea of what it's asking here, a trace? Does that ask make sense to you? What shape are the traces parallel to an XY plane? Um,
did it?
hmm? Do you roughly know what you're being asked to do here? Anybody? All right. Uh, so starting off, if we're asked for traces parallel to XY plane, that's sort of like saying, how do I put it? Um, I'm just going to draw a random object, not necessarily the object for this particular problem. It's going to be like a surface. Let's say that it's a sort of double-sided, like a double-sided paraboloid,
Hmm.
or like a double-sided bowl. So if this is X, Y, and Z, the motivation behind this problem is that they want you to sort of take the cross-sectional slice at multiple different Z values for part A, right? So if this is, um, just the way I've drawn it, each one of these cross-sections is more or less a circle, right? And the idea is that if you draw out a bunch of different, sorry, that wasn't very good. If you draw out a bunch of different cross-sections, yeah, it's going to be the further you go up, the larger the circle is going to get. The further you are to the origin, the smaller the circle is going to be. And this particular shape has a symmetry here where up and above, sorry, it's reflected across the XZ plane. So the stuff down here is sort of also the similar circles. And you can sort of get a feel for these as well by drawing these cross-sectional slices. Now, the idea here is sort of the opposite of what you're being asked to do. You're sort of being asked to do the cross-sectional slices first. You're sort of being said, okay, at Z is equal to maybe like 1, you get a tiny circle, and then Z is equal to like something larger, you're getting like a bigger circle. And then the further you go up, the larger the circle gets, right? And then you sort of do the exact same thing below. Uh, so if this is Z is equal to 0, you're sort of saying, okay, what's the pattern here? All right, the further you get away from the origin, sort of the larger the circle gets. And the idea here is that each one of these things is what they're calling a trace. I would probably prefer to call it a slice, but they're calling it a trace. And the idea is that you're sort of like taking all these images together and trying to reconstruct the double cup or the double this object over here. Does that kind of make sense? You're basically, each part of the problem is asking you to do these slices along some axis, drawing out a bunch of them, and then sort of doing this for the 3 different axes, trying to reconstruct this shape. Now, for this particular example, I only did this along the z-axis, which is parallel to xy. And it was kind of easy enough to see because the circle is kind of a nice, easy to think of shape. But if you were doing this for like the maybe if you were doing this for like the xz axis instead, it might look like this. You're kind of testing your visualization skills, but no, I'm sorry. It would probably look something like this when y is equal to 0. But then as you would start moving along, it would start sort of separating out like this. There would sort of be a gap. And for this particular problem, it's not as easy to visualize these parts. But I think visualizing the circles for this particular double bowl object makes it very obvious. And the motivation behind this problem is, okay, if we draw these slices, these traces from a couple different angles, hopefully by putting them all together, or maybe one is really easy to visualize compared to the others, but one way or another, we're trying to reconstruct the object by taking a bunch of slices. It's sort of like that old adage, like a bunch of blind men feeling the different parts of an elephant. And, well, that saying isn't a great example because the idea behind that saying is that they can't reconstruct it, but the hope for us is that we're going to try to reconstruct it based on individual slices. Does that sort of, at a high level, make sense?
Yeah.
Okay.
Kind of does, yeah.
Alrighty. Well,
so you said as we get closer to the origin, they get smaller?
Yeah, right. It's just for this particular shape, right? You can kind of see that for this particular shape, as you get closer to the origin, the circles get smaller. Now, this isn't always true of any surface. It depends. But we're going to just have to keep our wits about us as we go ahead and talk about a couple different surfaces. All right, so that was basically just a example that I pulled out of a hat. But let's get back to talking about the actual problem itself, or something similar to the actual problem itself. So 16x squared plus y squared plus z squared is equal to 16. All right, let's just rewrite that. 16x squared plus y squared plus z squared is equal to 16. So maybe one of the first things to do is it's talking about a trace parallel to the yz plane. Sorry, xy plane. Okay, so it's first starting to ask for xy, which is sort of saying, imagine that xy become your independent variables, and that you're doing this for a bunch of different planes, like z is equal to 0, z is equal to 1, 2, 3, and also z is equal to negative 1, 2, 3, etc. Right? So basically, it's saying that for this, remember with this talk over here, we were sort of doing a slice for each z value. We're doing something here, similar here. So, okay, the way we maybe start this is, okay, for z is equal to 0, this just turns into 16x squared plus y squared is equal to 16. We should know this from, like, 8th grade math, maybe? In just 2 dimensions, what is this? Do we know?
Is this a circle?
No, not quite. It's an ellipse. It would be a circle if the coefficient in front of x squared and y squared were the same. But what this looks like is I'm sort of drawing it at an angle because I want to like reconstruct it later. But,
wait, sorry, quick question. Is this for the xy plane?
Yes, this is traces parallel to the xy plane. That's right.
Okay, cool. Thank you.
Yeah. So for z is equal to 0, x squared plus y squared. So if this axis is x and this axis is y, this is sort of going to look like, all right, so if this is the value of 1, it's sort of saying this is an ellipse where the x-intercepts are 1 and negative 1, whereas the y-intercepts look to be 4 and negative 4. So it's kind of hard to draw, but like, how do I do this? It's sort of like longer than it is wide, right? The y-axis is sort of the long axis, the x-axis is a short axis. Yeah? And so that's for z is equal to 0. Now I'm going to do z is equal to 1, and I'm sort of drawing it like this because I'm going to try to like reconstruct it, mash it together later. But like z is equal to 1, okay, that just turns into 16x squared plus y squared. Well, I'll just do a step together, right? So if you z is 1, that just turns into, and you just move it to the other side, that just turns into like 15, right? So that's basically saying, if I'm not mistaken, that's basically saying it's almost the exact same idea. It's just going to be a slightly smaller ellipse. It's kind of hard to visualize, but just like, you know, pretend that I drew this one to be like, I'm going to exaggerate a little bit, but it's meant to just be a tad bit smaller than the one below it. And then as you get larger and larger, z is equal to 2 maybe. This turns into 16x squared plus y squared is equal to 12. So the idea is the sort of shape is preserved. It's just that it's sort of getting shrunk and shrunk. Right? I'm going to try to draw this one even smaller. And it looks like I'll skip to z is equal to maybe 4. At this point, with z is equal to 4, this turns into 16x squared plus y squared is equal to 0. Which basically means that at this point, it's no longer even an ellipse. At this point, it's just a single point at 0, 0. That's the only eligible point, because if x squared plus 16x squared plus y squared has got to be equal to 0, they both got to be equal to 0, right? If they were any other number, then the left-hand side would be positive, which would not work because the right-hand side is 0. So yeah, that's sort of the positive direction. The negative direction is exactly the same. It's exactly the same because x squared, y squared, and z squared were, well, they're all squared, right? So whether it's positive or negative, it's going to be symmetric. Which is to say that whatever I had over here, I should have the exact same thing over here. And maybe, in fact, I'll try to see if my fancy Windows Note thing can actually just copy paste this. Think this will work? Wow. Technology. Okay, yeah, that's cute. So that's for z is equal to -1. And this is going to be for z is equal to -2. I'm going to go down here and copy it. And then for the very last one, wow, that is so awesome that this works. Let's drag that down here. So that's z is equal to -4. So at this point, okay, there's two things to talk about. One is, are there any restrictions on the possible z values? Are there any restrictions on the positive z values? Excuse me, just on possible z values. Do you say no?
I say no for z values, yeah.
No for z values. Okay, tell me.
Oh, wait, no, sorry. Can it never be negative because it's squared?
Well, it can be negative, right? We already showed that for negative z, it's perfectly fine. It just looks like one of these.
Oh,
So
yeah.
it's a good guess, but what happens if we push z to be 5? What does this look like? It's already shrunk to a point. Can it go any further?
Yes.
What happens? Okay, what happens if it goes beyond a point?
It just is a smaller point.
It's just a smaller point.
Infinitely smaller point.
Well, no. This is already a single point already. No, it can't get smaller.
Does it disappear from existence?
Yeah, no, yeah, basically, right? And so that's the intuition, is that once it's already shrunk to the point of being a point, you just can't get any smaller than that, right? At this point, there's a single solution when z is equal to 4 or -4, and when you try to push z beyond that, then there's no solutions, zero real solutions, I should say. And how do you see this mathematically? Well, just try to plug in z is equal to 5 into the equation and see what you get, right? Try to plug in z is equal to 5 here, and then try to rewrite this, and you should probably see that you'll get something absurd. I'll leave that for you to try to think through. But there should be a nice correspondence between visually you can't get like smaller than a point, right? After a point you just have nothing. And over here you should get an equation that's not that doesn't have any real solutions. So play around with that idea.
So basically,
That makes
for any value of z that's greater than 4, that's a restriction basically.
Yeah, any absolute value of z greater than 4, yes.
Okay.
Because think down here too, it's all symmetric. Right.
Sorry, I have a question because I got here a little bit late.
Sure, what's up?
Can you just touch on, I mean, I understand that this is an ellipse and we're just like experimenting with the changing sizes, but can you just recap conceptually what your approach to traces is?
Sure. So by the way, this is recorded and it'll be online soon. But the sort of idea, I sort of started playing around with a situation where I started talking about a sort of double-sided paraboloid. It's sort of like two bowls back to back. And the idea here is that if you have like this paraboloid surface, the idea is that if you drew a bunch of like cross sections through it, you would sort of see that the intersection would be a bunch of circles, right? And the radius of the circle would differ depending on how close the origin are. You would get so closer to the origin is smaller, and further from the origin, the circle would be bigger. So the idea behind this problem is sort of asking you to do this process in reverse. It's sort of saying starting with a cross section by choosing various different values for z, and then looking at what the x. So basically, if you fixed z for each one of these planes, and then figured out what 2D shape the xy values would take, right? You would get a bunch of circles of different size, depending on what value of z you have, right? So this z is equal to 0. For this particular object would be just a single point at 0. But then as you get sort of further and further away, you get larger and larger circles. And what the spirit behind this problem is basically saying, starting with this, reconstruct the original object, right? It's sort of saying, instead of taking x-rays to look at individual slices, you're sort of, it's the reverse process. You're sort of like a bunch of blind men trying to feel different parts of the elephant, right? Each one of these is like a different part of the elephant, and you're trying to like mentally reconstruct what the elephant looks like based on a bunch of different slices of it. And what this rest of the problem, well, sorry, this is for one axis, but for this particular problem, it's kind of easy to see just from the z-axis. But for other problems, you might also have to look at x and y to get a better idea. That's the motivation. That's the approach here.
Thank you.
Yeah, sure. So that basically does it for, the first problem, right? You can also, well, it asks you to do this for the xz plane and the yz plane as well. But like at this point, I think it should be like kind of visually clear that like we're already dealing with kind of like a somewhat ball-like object. It's kind of hard to draw. Well, it's really hard to draw. Okay, yeah, that was terrible. Maybe it'll be easier to draw if I draw an xy plane. But I think the idea here is, if this is x and this is y and that's z, it's sort of like x is much smaller than the others, but it's sort of like, it's sort of going to look something like, something like that. Yeah, it's going to be a distorted ball, kind of like a football, basically. An oblong football.
I have a question.
What's up?
What is the question? Is the question asking us what's the shape that is parallel to the XY plane?
Yeah, I think that's what I was asking, right?
Yeah.
So it's basically saying, what are each one of these shapes? What are each one of these shapes? And we already said earlier.
It was an ellipse?
Yes. So if you imagine like stacking a bunch of ellipses on top of each other, maybe I'll reorient this drawing a little bit to make it line up with the drawings that we have on the left. So if this is x and this is y, I'm going to redraw it like this. X, y, and z is sort of upwards. This is still a right-handed coordinate system, right? Just check with the right-hand rule. But the idea is you sort of have the biggest melon here, and you sort of have like smaller melons, sort of like smaller ellipses on top. And then, okay, this was terrible, but this more or less forms an ellipsoid, right? It's sort of like a football. Yeah, I struggle to draw this, but hopefully you can kind of see that if you stack a bunch of these together, you sort of get a football, right? And the rest of the question asks you to do this for the other parts. So for I think the xz plane is pretty much identical to xy, now that I think about it, because y and z are totally symmetric in this equation, right? So the shapes that you draw over here should be like basically the exact same cross sections for xz as you had for xy. You see what I mean? And just from like a 3D football where one axis is, I guess it's more like a reverse football where the x is shorter than the others, right? So if like a normal football is sort of like round in the middle and long on the sides, this object is actually kind of like this weird reverse football where it's like really short on one axis, but then symmetric on the others. Maybe that's not the best way to explain it. You see what I'm saying?
Wait, you mean it would be short on?
Yeah,
on
it's the x-axis that's short, but the y and z are totally symmetric with each other. So if you try to sort of treat like y and z as neutral, how do I put it? So like a real life football, like y and z are perfectly symmetric with each other. So like what am I saying? Like the y-intercept and the value of the z-intercept are exactly the same. But for a real life football, it would be like really, really long, right? It would be really, really long because the x-intercepts are large. But for this particular problem, it's kind of different. It's like the x-intercepts are actually really small.
So the shape doesn't change when you switch the planes? When we switch from xy plane to xz plane?
Yeah. Those two happen to be exactly symmetric in this original equation, right? So drawing it out, you would get the exact same shapes. They just might be oriented.
It would be different with the yz plane.
What's up?
It would be different for the yz plane?
It would. Because now when you look at the yz plane, right? So 16x squared plus y squared. So now we're looking at yz. So xz is same as xy, but for yz, now we're looking at 16x squared plus y squared plus z squared is equal to 16. Now it's sort of like saying let x be sort of your parameter, whereas y and z are sort of your independent variables. So if you take, it's a little bit tough because the 16 is so exaggerated, but if you took a value of like 0 for x, you would just get y squared plus z squared is equal to 16, which of course is a circle, right? That's obviously a circle. And then if you chose different values, like maybe the intelligent way to do this would be to choose, no, let's not do this intelligently. That's boring. Let's just choose, so x is equal to 0. I don't know, x is equal to like a 10th or something. Then you would sort of get y squared plus z squared is equal to 16 minus, I guess that would be like 16 over 100 or something like that. Is that right? Wait a minute, 6x. So like basically the x can only go up to a value of what I'm trying to think ahead is like what's the maximum value x can possibly have here. And basically the idea is y and z has to be non-negative because they're squares, right? Which means that at minimum these two can be 0. So if you have 16x squared, basically if you're pouring everything into x, what's the largest value of x you can get? And that's basically a value of 1, right? This thing can't possibly go beyond 1 because otherwise the left-hand side would be guaranteed to be bigger than the right-hand side. So I guess x is equal to 1 is the largest possible value you could do here. In which case y squared plus z squared is just equal to 0. And that's going to be a little dot. Again, over here, it's sort of like a circle. And over here, it's sort of going to be like a smaller circle, right? So it's a similar idea where you sort of have the largest the largest area in the middle. And then as you go down or further away from the origin, it gets smaller and smaller until it shrinks to a point. But the difference is that these are going to be circles rather than ellipses. These are going to be circles rather than ellipses. So if this is y and that's z, and this is y and that's z, remember that, looking at this thing over here, y is sort of going into the page, x is going to the right, and z is going upwards. So each of these circles are sort of like, what do you call it? It's sort of like a slice over. It's really hard to draw. Let me draw like the football again. But you can kind of see that if this was a football with a large x intercept instead of a small x intercept, you could kind of see that like every single cross section is going to be like a circle. You see what I mean? Every single cross section. What do you call it? Like if you tried to cut it in half, is this lengthwise or widthwise? You would get sort of a circular base. You see what I'm saying? And that's sort of what this is. You just gotta sort of like mentally rotate this so that y and z are sort of like vertical. Can you picture that?
Yeah, so the width form of slicing, it has to be along the YZ axis because that's the only circular one rather than the
I think the word here actually is girth, maybe. Yeah. I think that's yeah, but basically like the girth, well, okay, the girth is sort of like the measure of length around the but like, the way, like if you imagine measuring the girth, the shape of that tape would be a perfect circle, right?
Yeah.
Yeah, that's the idea. So, okay, right, and these values are obviously going to be symmetric across the positive and negative. Sorry, these shapes are going to be symmetric across 0, right? Whether they're positive or negative doesn't really matter. But that's the idea. So, right, the shape for x is equal to 1/10 and negative 1/10 is going to be the exact same thing. And for x is equal to 1 and negative 1, it's going to be the exact same thing. So, okay, that was a lot of talk for a single problem. But that's the general gist behind one of these. And the hope is that once each one of these you do, the easier they get. Yeah? It's a lot of discussion. Yeah. Any questions?
Can you make a statement about, well, I mean, maybe there's not much to say. I was just noticing that the potential values for x are more restricted than the potential values for the other axes.
Yeah. We actually did talk about that, right? It's because let's say that this equation, instead of being 16x squared, maybe if it was instead 1/16 x squared, then we would get a situation like a football, because that would basically mean that the x-intercept would be really, really large compared to the y and z intercepts, right? Because if you instead plugged in 1/16 x squared plus y squared plus z squared is equal to 16, if you're like imagining pouring everything into x, that's essentially figuring out what the x-intercept value is. And that would be really large, because the 1/16 sort of like, I don't know, makes it smaller a little bit. But because it's rather 16x squared, that means instead of the x-intercept being large compared to y and z, now it's really small compared to y and z, and that's kind of hard to draw. That's kind of hard to draw over here. But it's sort of like a football, but like if you start from a sphere and stretched it, you would get a football, right? But we're doing the opposite in this problem. We're starting with a sphere, and then sort of compressing it instead of stretching it. It's sort of like a reverse football.
No, yeah, that compression comment made it a lot easier to visualize.
Yeah.
Thank you.
Okie dokie. Well, I guess we just continue talking. But to x squared plus y squared is equal to z squared. This is pretty similar. Yeah. We just start by looking at the traces of the xy plane. So for different values of z, What does this look like? If z squared is equal to 0, then x squared plus y squared also has got to be 0. So the only valid thing is a point here. But then if you did like z is equal to 1, this would turn into a circle. And then if you did like z is equal to 2, this would, well, I guess I shouldn't have drawn that one so large. Basically, the idea is it would just be larger and larger circles as you get away. So it's sort of the opposite of what we had above. Z is equal to minus 2. Yeah. So just from the first part alone, you can kind of tell that this is sort of a bunch of circles that kind of condense down to a point as you get close to the origin. But so it might look something like a bowl, or it might look something like a cone. Right? It sort of depends on whether these things, like how fast the circles get smaller. So we're not totally sure yet. We basically got to look at the other cross sections to figure out whether it's this or whether it looks like this. So far, so good. But it's gonna look like one of these two.
So the only restriction here is 0.
Yeah, I would
Right.
say that z is not restricted here, right? Z could like I know what you're saying. You're kind of fixating on when it goes to a point here, but like on either side of this point, like going above or below, are totally valid. So really, z is not restricted at all.
Okay.
Right? And visually, this is basically saying that you could, if you wanted really, really large values of z, you would just go really far out and you could find something on the cone or on the bowl. Right? So I would say there's no issue there. Okay. What's up? So now looking at...
Sorry.
Yeah, sorry, go ahead.
Well, I was just wondering if we conceive of this as two shapes that are touching, or is it one shape that happens to get as small as a point in its center? Bottom?
This is kind of a semantical question. Like this single equation would describe both the up and the down, as well as the sort of point in the middle.
Okay, so it's the entire hourglass or cone.
Yeah. Oh yeah, that's the word for it, hourglass. Why did that word escape me? Okay, so now to sort of distinguish between the two, now we've got to look at sort of the XZ traces. So that's basically when... Okay, so above I thought it was easy enough to see, so I wasn't writing out the equation each time, but now I will. So for when... shoot, what's this happening? When y is equal to 0, this is when x squared is equal to z squared. What does this look like? X squared is equal to z squared on a... maybe let's call this an xz plane. What does this look like? Go on. This is just x is, or maybe this is just z is equal to plus or minus x. So it looks like that. Yeah?
Yeah.
Yeah. So in fact, this we're pretty much already done
So
because... What's up?
So just a line.
So just... Yeah, it's sort of like a line both with positive one slope and negative one slope. So like kind of
Okay.
two lines. So already we're kind of done because this information right here lets us distinguish between whether it's the cone or the hourglass. Right? If this is the cross section when y is equal to 0, and this is sort of like x, y is sort of in the page, and then z is sort of upwards, is it going to be the cone or the hourglass? Which one does it look
Cone.
like? Yeah, exactly. It looks like the cone because the point of intersection is jagged and sharp. Yeah, it looks exactly like a X down there, as opposed to this like curving thing.
If it were the curving thing, then would it just be x squared is equal to z, plain old z, or?
Yeah, that's right. That's exactly right. Actually, if it was the other one, it would have looked like plus or minus x squared. So it would have just looked like two upside down parabolas. See that? You can kind of see how like this is the cross section for this thing. When y is equal to 0.
Mm-hmm.
Yeah. Anyways, at this point,
So
what's up?
if for like y equals 1, it would be x squared plus 1 equals z squared. So that would just mean that we start at like 1 point above, same intersection, but just 1 point up.
Yeah, it's harder to visualize, right? Because this turns into z is equal to plus or minus x squared plus 1, I think. Yeah. And I actually wasn't sure off the top of my head what this looks like. But I had to basically put it into a graphing calculator. But it kind of looks like it looks like a very soft parabola, for lack of a better word. Yeah. So in fact, we didn't really. Yeah. Okay. The questions were typically asking about for an XZ trace what the restrictions on Y are, but it doesn't really ask about the restrictions on Z itself for an XZ trace. But you can kind of see here that there is going to be a restriction, right? There is going to be a restriction because for Y is equal to 1, Z can't equal 0. But yeah, it's sort of this is the point where it gets sort of hard to visualize, right? But the idea is that as you increase the value of Y, the graph kind of looks like these almost parabola looking things that just sort of get away. But you can kind of visualize that. This might take, more visualization skills than average, but like it's basically saying, okay, for Y is equal to 0, that looks exactly like this cross right here. Yeah. But for Y is equal to 1 or minus 1, you sort of have to like zoom in a little bit. And it's really hard to picture because now you're not right. That's not like one of the typical points of intersection of these cones. It's sort of kind of on the slope of the cone. Like, can you kind of visualize how it looks kind of like that? Right? There's not going to be any jagged edge because Y is like into the page a little bit. Anyways, if you can visualize it, that's great. If not, it's not the end of the world.
So then what again would the restrictions be for y?
I don't think there are any. Yeah. No matter how you change this equation, for this equation, you can adjust any value of y, and x and z can just adjust as well to accommodate. So I don't think there's any issue. I don't think there's any issue at all. Y can be as small or large as you want it to be. Okay, so I think that covers that. And then I think the last one is the YZ plane is exactly the same as XZ. Is exactly the same as XZ. Because again, just looking at the equation, you can kind of see that you can see that x and y are totally symmetric in this equation, right? X and y are totally symmetric, so when you change this x, sorry, what did I say? When you change this x into this y, and z is the same in both cases, it's exactly the same shapes that you'll be getting with x and y swapped. And as always, I like to relate the equation to the picture. But you can kind of see in this picture right here how x and y are kind of symmetric with each other, right? The xy cross section, each one of them is a circle. How do I put it? And sort of the circle has constant radius, so it's sort of the x-intercept and the y-intercept are the same size. As opposed to z, which just has totally different behavior in this graph. Good?
Yes.
Okay, all right. Yeah. So what else is there to say? Oh gosh.
So I'm assuming there's no restrictions on x again. On
Yeah,
this one as well.
it's you're talking about the last one where if you are talking about the YZ traces, the restrictions on X, yeah, it would be exactly the same as on Y over here, which is nothing. Right? And just like pictorially, you can kind of like see it, right? Because like if you want X to be as large as possible, what a restriction means is, can you find some point on the cone that has a value of that X? And it's like, yeah, if you have like X is equal to some large value like, 10,000 or something like that, it just means you got to search really far out. But, if you look far enough up on the cone, you can do it, right? There's nothing stopping you from just going a mile out and saying, hey, this is the point where X is equal to 10,000, right?
Mm-hmm.
But whereas with the ellipsoid or a sphere, you do have that restriction because, right? Excuse me. You do have that restriction because above like, z is equal to, what is this, like 4? Or yeah, above z is equal to 4, like there's literally just no ellipse here, right? If you look for z is equal to 4, no matter how you vary x or y, there's just nothing here. See what I mean?
Yeah, it just became too small. Well, it got smaller and smaller until...
Yeah, it shrank, disappeared, right? No more solutions for when z gets too large. Alrighty, so the last one is actually really hard to picture. And, I mean, I feel like it's kind of sadistic to give you this one, but okay. For this one, you just kind of gotta ham through it. I don't know if that's a phrase I just came up. Yeah, so if they're asking for things parallel to the XY plane, and, we're just going through Z, I don't have any great wisdom here other than just to draw the shapes like we did before. And for this particular one, it's really a pain in the butt because I don't think it becomes particularly clear, right? So when Z is equal to 0, this just turns into x squared is equal to y squared. And that just looks like a cross. Oops. And then when Z is equal to, say, 1, this turns into x squared is equal to 1 plus y squared. Or alternatively, actually, no, let's put it in terms of y. Y is equal to plus or minus square root of x squared minus 1, I think. And that's, I think that looks something like... Wait, what does that look? I think that looks kind of like that. Yeah, something like that. Maybe? Anyways, go play around with those ideas and just draw a bunch of them out.
Are you saying we have different graphs for different inputs?
What's up?
Are you saying we have different graphs for different inputs? We have different...
Well, no, I'm saying sort of... At this point, z is not an input, but a parameter, right? So when you choose z to be equal to 1, you get 1 is equal to x squared minus y squared. And that looks like y is equal to plus or minus square root of x squared minus 1. So you're sort of getting a different graph for each parameter, each trace.
Okay.
I actually don't know what this is going to look like, and I should probably look this up before misleading you.
X squared so for all 1. Of like the last questions, A, B, and C, both the z values, y values, and x values, there's going to be no restrictions, right?
Yeah, I think so. At a glance, that looks true. At a glance, that seems to be true. Because, like, I'm just looking like z can be anything, right? Like plus a positive huge number or minus a huge number, and x or y will just change to accommodate that. And I think that's similarly true for x or y. Yeah, if x gets huge or very negative, then z will just change to accommodate it. If y is huge, z will change to accommodate it in a negative direction. Sure, yeah. But yeah, I think that's the idea. The final, I won't spoil it, but the final shape for this one I think is kind of terrible. I don't know how you're supposed to draw it in 2D, but I guess just do your best. This one's hard. Very hard to draw and visualize. Yeah. So, if xy sort of looks like these, looks like an X that sort of like splits across as you go further and further out. Yeah, you do the same thing for YZ, and unfortunately now there's no more I don't think there's any more symmetry in the problem, because X, Y, and Z are all different in this one, are all genuinely different. And for the previous problems, they weren't that bad because we had symmetry and they were kind of easy to see. For this one, you genuinely have to draw 3 different sets of traces and try to like mush it together in your mind, and it's kind of awful.
So it's something asymmetric that doesn't look that continuous.
It's
like, I know it's continuous because there's no restriction, but I'm just general.
Yeah, I wouldn't. The fact that the fact that this piece over here has this like discontinuity doesn't mean that the entire surface is discontinuous, right? Because
it might just be like a little dip.
Well, like look over here, right? It's because with a cone, when you the cone, right, is continuous is a weird word, but like connected. There's no like from any point in the cone you can get to any other point in the cone, right? And the reason the cone had this like weird thing going on over here, but that's just because when you set a value of y to be like 1, you're sort of taking a cross section of the cone like a bit deeper in. So even though the cross sections aren't connected, like the actual surface itself is. But yeah, you're gonna have to draw these out a little bit. It's gonna suck. Right, this turns, so for varying the different values of x, this turns into x is 0, this just turns into z is equal to minus y squared. For x is equal to 1, this turns into z equals 1 minus y squared. X is equal to 1. Z is equal to minus 1 minus y squared. So this just looks like a series of parabolas. Oh shoot, this is just gonna be 1. Because x gets squared. Yeah, this looks like just a bunch of parabolas to me, right? So the middle one is just a negative parabola. Ugh, what's going on? Whereas over here, the sort of parabola gets raised a little bit. So what this sort of means is from the x, y... God, this is so hard to picture. From the x, y, x, y, and z plane. This is sort of like saying okay, maybe this is the easiest way to picture it is using the YZ traces, but this sort of looks like a parabola that's sort of in the YZ plane. And then as x gets larger, it's sort of like the parabola gets raised up a little bit. So it's kind of like a, how do you put it? It's almost spoiling it, but this is sort of like, imagine sitting on like a horse, on a horseback, right? Like, what is a horseshoe? You know those things they put on horses, like a horse seat or something?
A saddle.
Okay,
Yeah.
that's spoiling it, but okay. Yeah, right. It's sort of like a seat. It sort of like dips down, and then your sort of like legs go off on the side here. Right? Can you imagine this? Just imagine like a person sitting on this thing with their legs sort of hanging off each end. Huh?
This is weird.
This is weird. Yeah. No, I guess with these parabolas is probably the easiest way to see it, because like this to me is just a pain in the ass to visualize, in my opinion. Like I don't know what the hell to do with this. But with a bunch of parabolas sort of stacked next to each other, sort of rising up as you go away, I think that's easier to work with. Yeah. And the parabolas themselves, the sort of y-intercepts of the parabolas change themselves in a parabolic way, if that makes sense. Like if you just put together all the y-intercepts, like this shape itself is a parabola. So this shape could almost be seen as like a bunch of parabolas dangling off a big parabola. Yeah. You guys got it?
That's pretty neat.
Yeah.
Yeah, I think that's. Yeah.
Yeah. I don't even know what is left. The XZ plane. Wow. Wait a minute. Is there a way to view this in terms of positive parabolas? How the hell? With the y being varied? Okay, I don't even know how that would work. So with y being 0, this would turn into like z is equal to x squared, and then c is equal to x squared minus 1. So I'm just trying to think about this now. This, we could, with the yz traces, we could view these as a bunch of downwards facing parabolas, but supposedly we should be able to get the same shape using a bunch of upwards facing parabolas as well, and I'm just kind of blowing my mind because I'm not seeing it. But if we assemble all these together in the I'm going to draw it slightly differently this time. This is x, this is y, and that's z. So y is being varied, and we just get a bunch of oh shit, wait a minute. What the hell? Okay, I guess it's a bunch of detail that I didn't really put in there. But like, I don't know, I'm not convinced. What the heck? Anyways, somehow it's not quite giving me the same shape, at least when I'm visualizing it in my head. But go through the process and try to draw what makes sense to you. Yeah, this would make sense to me if this was increasing rather than decreasing, but somehow it's not. Anyways, I guess that's all I have to say for today. Any questions?
I don't have any questions.
Sure. Okay, very good. All right, folks, I'll post a link to the recording, and yeah, go ahead and have yourselves a good night, and let me know if there are any questions.
Well, thank you very much.
Sure. Take care, y'all.
Thanks. Thank you.